Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Great. Soleil Tamati from Michigan State University, and the paper was co-authored by Jason Van Eaton, who's on vacation right now, I think. And so I guess I'll let Soleil take over.
Okay. All right. Okay. My name is Saleh Tamadi, and I just finished my second internship with Microsoft Research, working with the Conference XP team, and I also just finished my master's at Michigan State University, and part of it, this is my in my master's thesis. So this talk, so I see lots of familiar faces from the Conference XP workshop. Parts of this work is reviewing what I've done, what I presented in that talk, and then continuing on a game theoretic analysis of that. So the first is my talk is about a tool that we have been developing at Microsoft Research to combine the benefits of application layer multicast and the IP multicast together. And this particular presentation is about how would this change the economics of multicast. So you all know about what multicast is. It's a single to multiple destination type of traffic, and IP multicast is an efficient way of implementing that. So if IP multicast is not enabled and you want to send something to multiple sources, you have a huge bandwidth at the source that you have to consume. And if you do have IP multicast, then you don't have to pay that much for the bandwidth at the source. So it's very simple. So although IP multicast has been around for a long time, the deployment is still behind expectations, and we'll see why. So there are a few problems addressed by researchers in this area. The first and probably the more important one is the pricing scheme, is that the multicast violates the traditional way of pricing in the internet. So if I just go back one slide, you can see this node here is being paid by the source for, let's say, one stream, but he has to pay an uplink of 2 streams to send it out to 2 different routers, and then you see as goes on, it gets to here, and this router is sending it to 3 users. So the traditional pricing is that a router, when it's receiving one stream, then it will make up for the cost of that by getting the same amount from the user in terms of money, and then he will make up for that by doing it the same way with his provider. So that is an important problem. The other one is the chicken and egg problem, which is you talk to people about why IP multicast. You talk to administrators, network administrators, about why IP multicast is not enabled. They say there's not really that big of a need for us to enable it, right? And then you go to users why you don't need IP multicast, that there's no good application for that. And then you go to software developer and then tell them why there's no good application. It says people don't need it, right? Or even if they do, there's no good backbone to support it, right? So why would they do that? So the alternative to IP multicast, which has been around for quite some time too, is the application layer multicast, which in this model for multicasting, the protocol doesn't depend on routers. Instead, the users will make some multicast tree among themselves and try to distribute it in an efficient way. So the bad thing about the application layer multicast is that it creates a lot of delay, and that's what it makes it not a good choice for at least conferencing or real-time collaborative works. So what we have came up with is a multi-reflector service, which takes advantage of IP-Multicast where it's available, and where it's not available, it will use the application layer multicast scheme. And so you could see on one hand, so if IP-Multicast is not supported anywhere, then in the worst case, we're back to application layer multicast. But as we study later in the slides about the effects of having such a tool, we'll see that the network administrators, based on their traffic load, may decide to enable IP-Multicast to lower their traffic given such a tool, and then we will see IP-Multicast getting enabled more and more on the internet. So just to give you a feel of what this tool does, say there are a few places in US that want to do a collaborative work together, so they all want to collaborate with each other. So we separate these, we partition them into 3 different levels, or we partition them into the IP-Multicast islands, we call them, which are the ones that IP-Multicast does work among them, which say down here we have Internet 2, which IP-Multicast should work, and then we have up there MBone, which supports IP-Multicast, and then let's say there are other islands too which support IP-Multicast internally. So now the reason that I showed the map initially, and now I'm showing it in clouds, is that these computers are not necessarily in the same location, right? So Internet 2 has drops on West Coast and East Coast, but we're showing all the ones that do support IP-Multicast among them in one cloud. So this implies that different computers on each one of these clouds have different networking characteristics. So we have to have that in mind for optimization purposes later on. So let's say these are the set of users that are currently interested in a particular stream. So what we do for the multi-reflector services, we put 3 computers or 3 services on each one of these islands, and then once one of the users multicasts something, it gets to one of the reflector will send it through the other 2 reflectors through application layer multicast, or basically IP unicast, not IP multicast, and then those reflectors will send it on their island. So this is simple. So we even make it easier for deployment, that we don't require a separate machine to run a reflector service. Each one of the participants could be a reflector. So once one participant from one multicast island becomes a reflector, then that island will merge to the other islands, and that means they will receive the same traffic through application layer multicast. So this is the same thing. So there are many optimization problems that would raise with such a model for multicasting traffic among users, which I had another talk on this, and we have a paper in Infocom 2006 on this topic, which is not the focus of this presentation. But here are some of the results that we had so far on this issue. So now the question is, what would happen if we could have this tool deployed for every user that is interested in a multicast session or a collaborative work. So how would this change the economics of IP multicast, which has been, as I explained earlier, it would violate the traditional pricing. So we want to take a game theoretic approach to this this model and try to analyze it through a game theoretic kind of model. So our players in this, once you want to analyze it with game theory, you have to have players. Each players have to have strategies. The strategy of each player should affect other people's strategy, and then you'll look at the set of outcomes and see which one would be the desirable outcome, and how would rational users decide their strategy to get the best benefit out of it. So the players in our game are the network administrator or the routers. So basically, the routers are not at this moment a smart router which decides, what would happen if it turns on or off IP multicast. Would it make their bandwidth usage higher or lower? So basically, in reality, it would be the network administrator who could think of what would happen if I would have enabled IP multicast or disabled it. Then the available strategies are to first strategy is to enable IP multicast everywhere. So that means a router or a router operated, administrated by a administrator will enable IP multicast on all interfaces for the router. The second strategy is that the router would be IP multicast enabled internally, which is, let's say, for our university, Michigan State University, IP multicast works all internally, but no traffic, no IP multicast goes out, or no IP multicast traffic comes in. Basically, our internal IP multicast works, the external doesn't work, because that's when the university has to pay to the network providers to have IP multicast enabled. And then the last one is that IP multicast is disabled both internally and externally. And the cost of the players is their routing traffic. How much traffic does a router have to route? So if enabling IP multicast or disabling will change this number of packets it has to route, then that would be a factor that the router would decide that, oh, I'm benefiting from enabling IP multicast or disabling it, and that's what I'm going to do. So we'll in this presentation, we were looking at a very simple model, and we're looking at two routers and a set of users directly connected to each router. So first, let's look at the first strategy and see what are the costs for each user. So you see, as if all of these users are in, so all these circles are users, and this one up left is the source. So it sends the traffic through the router will multicast it back and forth and to everyone. So based on that, the cost is 1 in and M out if there are M users on the side of router P1, and the same for the other router. You see there's 1 in and N outs. So let's look at the other strategy, which is P1 will disable the external interface. So what would happen is that it will send the traffic there, it will get multicast back to all these users, and then it has to send an extra packet to go to the router to this destination, and then this user will multicast it back. So these two pink lines show the extra traffic that is going other than the traffic that was going just for pure IP multicast. If we had, so there are 2 more packets getting routed by these routers, and that's the extra cost. You see here each one of the players is routing one more packet. So let's look at now what happens if player 1 disables all the interfaces, both internally and externally. Oops. Okay. So the user will send it to this user will send it to the other one, this will send it to the other one, it will go all the way to the other. So this is basically what application layer multicast does. And this is the worst case scenario in terms of the routing usage. So in this case, the router P1 has M ins and M outs. And so the last case is that if both of them have disabled all their interfaces, so it's clear how it will work. It's just like the same thing, and the difference is that once it gets to the other side has to do application layer multicast too. So application layer multicast is not just on the P1 side, it's on P2 side too, and that's where both of their costs comes to M in, M out, or N in and N out. So if we look at all the outcomes or all the profits, or in this case it's not profit, it's cost, see what is the minimum cost, or how should the players play to get the minimum cost. We see if both of them enable all their interfaces, we'll have what is called the weakly dominating strategy. So the definition of a weakly dominating strategy is very similar to a strongly dominating strategy, which is a strongly dominating strategy would minimize my cost irrelevant of what other people do. So I have one strategy which is always minimizing my cost. So in this case, that is not true. The reason for that is that if I am now player 1, so if player 2 enables all interfaces, I could get to this point, right, by enabling all my interfaces too. But if player 2 decided not to do that by going to disable its external interface or all interfaces, then I'll go to 2 and M, right? So that's why this is not called a strongly dominating strategy, but it's a weakly dominating strategy, which means it's my best bet to do this, but I may not be guaranteed this outcome. So this was a very simple analysis, a game theoretic analysis of how would this tool affect the economics of the IP multicast, and how it may change the behavior of network administrators and their decisions to either enable or disable IP multicast. So in conclusion, if disabling or enabling multicast internally does not affect the outcome of other users, this is one thing we learned from here, is that if I change whatever is happening internally in my organization, that doesn't affect the outcome of other users. The other way of saying this is that if I want to get better performance, I have to enable my external interface. That's the only way that I may be able to get better performance. I may not get it though, but that's the only way that I could get affected by other people's strategies. And so in conclusion, this simple model, we show that a rational user, which we can't always say rational, or there are other factors. It's not just the cost. It's other things too. Is like there are other factors we haven't considered. Let's say the IP multicast is known to be, to damage the network, to have bugs or things like that. So there are things that are around which we are not taking into consideration in this model. But looking at just the routing costs and the traffic costs, we could conclude that a rational user, based on just this element, should decide to enable IP multicast. And my acknowledgement is to Dr. Shapiro, who I worked with him on on this problem, and my Microsoft Research and Conference XP group, which supported me to do this kind of research, and my advisor, Dr. Rada. Thank you, and any questions? Yes.
Have you looked at the networking protocol used by Skype? Have you had a chance to look at that?
No. In what context is that?
Well, so one of the things that they do is, which I think is similar, at least related, you might want to look at, is that everyone who participates becomes one of these nodes that can be any one of the following. So if you're behind a NAT, then you have to just transmit out and you don't get any choices of things. If you happen to be on an external IP, well, then your machine is used to route things because you join.
Mm-hmm.
And so the idea being that instead of changing the sort of cost piece is that by participating, everyone sort of implicitly agrees, I'm going to, if I'm outside, I might be a multicast router. If I'm inside, then I'm not. And, and then you get sort of this full connectivity without setting up servers or routers or any sort of policy ahead of time. It's part of everybody's fabric.
So if I understand right, this is it all unicast based, or
Well, it could be the model. What they implement right now might be unicast, but the model doesn't really matter. The model is that wherever you happen to be, it actually does network tests to find out, can I get from A to B? If I can't, then do the following. Or if I'm able to get from A to B, well, then I'll also route other people.
Okay, what is the name again? I haven't.
Skype, S-K-Y-P-E.
Okay.
So we look at it for AG stuff because Skype's well known now for their network level as being able to get over almost any network problem that's out there.
Yeah.
I mean, it adapts.
They try UDP, they try TCP, they try different port ranges.
A lot of their stuff is proprietary, and they didn't publish exactly how they did it.
Yeah.
Okay. Yeah, at least I didn't see it in the research literature. Maybe it's a commercial or something available.
There's a technical paper where some people reverse engineered this.
Exactly.
Okay.
That's how it's described.
Okay.
You can, if you Google it.
All right. Thank you. Any other comments? Questions? Okay. Thanks.